Welcome to the Quantum Perspective Seminar Series, which is hosted by the WitsQ Quantum chapter and IBM Quantum in collaboration with SAQT. I'm Nikita, and I'm from the WitsQ Quantum chapter. It's great to see you all here today, joining our session on quantum learning meets quantum crypto. We're joined by Dr. Mina Doosti, who is from the Quantum Software Lab at the University of Edinburgh. Dr. Doosti works on the intersection of quantum machine learning and quantum cryptography, and today she will walk us through how these fields are connected. She'll also share new insights on the limitations of quantum and classical cryptography and how new constructions are being designed in the quantum world. The talk will run until 4:15, and it will be followed by a Q&A session. Please join me in welcoming Dr. Mina Doosti.
Thank you so much. Thanks for the introduction. I'm very happy to be here and talk to you guys about some stuff that I work on and I'm really passionate about. So sharing my screen again just to make sure everything still works. Can you see my slides?
Yes, we can.
Okay, perfect. So I'm like full screen, so I cannot see you guys. So if you have questions in the middle, please, unmute yourself and ask me. Otherwise, I won't see you like having hands up or anything. Okay. So I will talk about this this topic, essentially, like a lot of topic. Essentially, this is going to be a very conceptual talk. So I'm going to start very like slow, and I'm mostly trying to give you some ideas and perspective about how these things can be linked and how like you can find like exciting questions in the intersection of quantum learning and quantum cryptography. So that's the idea. So apologies for the expert if this is not a very, very technical talk. Okay. Before I start, this is Quantum Software Lab. Not even an updated version of all the people there. So we're a very big lab now, based in Edinburgh. And so like we're around like 10 faculties in different departments, mostly in computer science, but also in physics and chemistry. And I'm one of them, and the rest of the people are like postdocs and students in the lab. So yeah, we're also very happy to have people for a visit and things like that. So let me know if you're interested. Okay, so I'm going to, as I said, this is a very conceptual talk, so I'm going to start very, very conceptually with a very, probably maybe boring sounding question that what is learning? Because I'm going to talk about learning, so I want to tell you what do I mean by learning. And so, as probably many other things, it really depends on who you ask. And so I'm going to give you today two perspectives about like how to think about learning. So if you ask a physicist, so you guys were asking me before, what's my background? So I'm a physicist by training. And with a physicist mindset, you see a phenomenon in the nature, right? So you see that, okay, we as creatures learn. So you observe that this probably has to do with our brains, and we want to figure out how the brain works. And the way physicists think about this is to think that, well, there should be a mathematically describable rules or pattern in probably particles or like something in a space-time that causes this phenomena that we call learning. And we want to learn that. And this is somehow, in a way, how neuroscientists think about the problem of learning. So they figured out that essentially our brain has neurons, and these neurons have like some firing patterns. And I really like these two pictures. This is the first picture of a neuron, and the right-hand side is the first depiction of a neuron by this scientist called Ramon Cajal, who's basically one of the fathers of neuroscience. And well, the point is that they were trying to figure out how this like complex system that is our brain works and leads to the phenomena of learning. So this is the question a physicist would ask: what are the rules of patterns and processes that like allow us like process information? Well, the problem is that this is a complex system, as I said, as we know, and it's very hard to understand. So we're getting closer and closer in understanding this, but we're not there yet, even now, after so many years. There's a different perspective to learning. You can be a computer scientist and think about it in a different way. And the first question a computer scientist would ask is that how something as complicated as learning can be modeled. And well, if you would ask Turing, for instance, he would say that, well, anything that's computable can be modeled in a, let's say, Turing machine. So what if we want to make a machine that learns, but it doesn't necessarily have to be exactly like our brain. We just want to model something that mimics this like behavior of learning. And well, turned out that this is a way easier way to think about learning. And there are actually ways to describe and abstract this process. And I would say, like many people, that this was the birth of a huge field that now has like affected all of our lives, and that's machine learning. It was just like this shift in the perspective that maybe we can think about learning in a different abstract way. And this is the way, even though again I was originally a physicist, I'm going to take this computer scientist perspective to learning, and I'm going to tell you what do I mean by learning when we think about it in this way. So yeah, let's make learning very abstract. And this is essentially what learning theory would do. It will give you a way of like abstracting the concept of learning and studying as a problem. And I like to see learning theory as a cookbook that you can pick different ingredients and you can merge them together so that it gives you like a well-defined learning problem, and then you can study that learning problem. So what are those ingredients? We can like figure it out together once at a time. The first thing that we understand when we want to think about learning is that, okay, there's something that I want to learn. So there's an objective to the learning. It can be many things, like I want to write an essay, I want to play guitar, whatever. And I abstract this whole concept of what is it that we want to learn in something that I will call unknown target object. So I have an unknown target object. Mathematically speaking, this can be a function or a distribution, especially in the classical setting. And I want to learn that. So I don't know it, I want to learn it. The second thing that when we think about learning, immediately comes to our mind is data. Like we are not learning out of nowhere. We usually start from somewhere, we gather data, we process data, and that leads to learning. So this data can be, again, many, many, many things. But if I want to abstract this, I can think about it as some samples of examples of the unknown object that I'm trying to learn. Is there any better formal way to describe this? Yes, computer scientists have this concept of oracle, where like usually you can like have it in algorithms and cryptography, but oracle is essentially an abstraction of something that has the knowledge of some like unknown underlying object. And if you ask a question, it would give you like answers about that. So in our case, if I have a function, for instance, if I ask for a value of a function on an input, then the oracle can give me the output. And only the oracle knows the function somehow. I don't need to know it. So oracles are usually good tools to model like samples and examples. Then the third important ingredient of learning is how do I know that I learn, right? So you need to have a measure to say that, okay, now this is good enough. This is what I learned. So it could be like when I write a good essay, so I maybe put some goals and I say, okay, when I reach that goal, then I learned, or yeah, so I can gain some level of confidence. Again, if we want to abstract this concept, we can think about it as a measure of success and failure. And again, if we want to abstract this or make it even a bit more mathematical, we can think of this as some notion of distance between the real object, like this guy, and the one that you learn, which we will call your hypothesis. So with these ingredients, now I can define a first formal definition of learning. What is learning? So learning is a process that finds a step-by-step, so it's an algorithm in a computer sciencey way, if you think about it, a close enough hypothesis, and this closeness is with respect to some selected measure, to a target object given certain number of samples or data. And it's It's as simple as that. But this simple way of thinking about learning gives us a lot of tools to be able to understand how hard is learning, how difficult it is, how I can do it, how to design algorithms and things like that. So if I want to make this a little bit more formal, you can also describe learning as a map that goes from a set of like a space of instances to a solution space, essentially to a hypothesis, and this hypothesis lives in a valid solution space. And the validness of this space you will you essentially like characterize with respect to the distance that you pick. So you go from like a so this function, this unknown object, which let's say in my previous example is a function, lives in the surface of data, and there's a map Z that brings this to a target space, and in this target space lives the space of a valid solution, and this is where my hypothesis lives. And this map Z is exactly learning. That's what learning happens. Okay. So now that I have this like ingredients of learning, I can design different learning problems, or I can like study different learning problems. So in a way, I can now cook with these ingredients different recipes. So let's see some very simple like examples from learning theory. Two very common oracles or way of modeling data or samples in classical learning theory are something we call example queries or membership queries. So essentially in one of them, you ask the oracle to give you some data, the oracle samples some input from the distribution and gives you X and F of X. In the other way, which we call membership queries, you can ask the questions yourself and the oracle will give you the answer, F of X. Simple as that. And just with like these two, I can define like three different instances of a learning problem. So the first instance of a learning problem I can define this problem, exact learning a Boolean function. Like assume my unknown object is a Boolean function. And I want to learn it exactly, which means that I want to have a hypothesis that for all X, when I look at my H of X, which is the thing that I learned, is equal to F of X. And I can do that with using both example query or membership query, depending on which like data access I choose. Well, this sounds nice, but it's a bit too tight because like I want things exactly, and this is deterministic, so it's not maybe like the most realistic model for learning. And then there's a second problem, which you probably heard about. It's very famous in learning theory. It's called probably approximately correct or packed learning. Here you allow for the learner to be probabilistic, so be sometimes wrong, sometimes right, and also the answer to be approximately close to the answer. So you kind of like, you pick some simpler distance measures, like more loose distance measure than just like strict equality. And then there's like another level of learning, which I change again my access model. I'm still trying to learn, let's say, Boolean functions, but I'm learning from like the statistics, not directly from input and output of the function. So I will talk about this later. I just wanted to mention that like already from like very simple target objects and simple example or sample access models, you can define like different variants of learning problems, and these are already very powerful to study learning. So the second thing we'd like to usually understand when we're doing learning theory is that how hard is a learning problem? And so what do we mean by that? Usually we have two figures of merit. The first thing that you'd like to understand about the learning problem is that how much data it needs, like what is the query or sample complexity. And the second question is that, okay, now after I know how much data it needs, I also like to know usually, if I want to run it on a computer, that like, what is the time complexity? How long would it take to run? And when we say something like a learning problem is hard to learn, it means that there is no algorithm that can learn it better than some like complexity, essentially. Yeah, so the important point about that is that lower bounds in learning, it will give you some very fundamental understanding of a problem. So it's not about like am I like a smart in picking my algorithm? It will actually tell you that there's like fundamentally something hard about this problem. And when we say something is easy, it usually means that we have an algorithm that solves this like learning problem with some efficient size database and in efficient time. So if you have an algorithm that solves the problem and it's running in efficient time, polynomial time usually, then you say that, okay, this is easy to learn, essentially. So far, anything I told you was classical and classical learning theory. But you can bring the same mindsets now into the quantum world. It's just that now we have a lot more options. So you have the classical learning theory. Now you can think of exactly same questions, but your algorithm, the ones that learn this map, can be quantum. And then you can bring even more quantumness to it. So you can think that the target objects that I want to learn are still classical. So I'm still trying to learn classical functions or distributions, but I'm learning them from quantum data. What do I mean by that? I mean that there's some oracles that gives you like a quantum version of your data. So for instance, for a function, maybe it gives you like your function you can create and it gives you the answer in superposition and things like that. So learning classical object from quantum data is the next level of quantumness. And then there's also learning quantum objects. And by quantum objects, I mean usually like either quantum state or quantum processes, that they could be channels or like unitary circuits and Hamiltonians. I would count all of these things as a subclass of learning quantum channels and processes. And so it's kind of like the same picture of the cookbook and the recipe. It's just that now you have more ingredients and you can like come up with a lot of like different learning problems. So for the purpose of this talk, I will mainly focus on the last part. So learning quantum objects when the objects are actually quantum, because this is the like one of the nicest parts that will connect to cryptography. All right. Do you have any questions so far? I'm going to go to the next part of my talk. Okay, I'm not hearing anything, so I'll continue. I'll take the questions maybe at the end. All right. So what is the difference, or like how do I connect these things that I just told you to machine learning? Because probably a lot of you guys, you're maybe more comfortable with machine learning. You know how it works, but like how does this two picture like come together? So let's have a look at that. What I would argue is that what machine learning or practical learning is just a heuristic version of this like formal problem that I described to you. So you still have an unknown object. This is usually again a function or distribution, but you don't usually know your concept class. So you don't know the set exactly of where this function or distribution coming from. Sometimes maybe you know, but most of the times for like most real life problem, you don't know that. Then you have data, you have samples from these objects, let's say faces of cats and dogs and like things like that. But these are like real world data. And so usually you kind of like map this data to some mathematical object that you know how to work with, for instance, vectors and matrices and things like that. And you still have measure, but you have an empirical version of this measure. So you have this like empirical loss or cost functions that like people use in machine learning to kind of like capture if they succeeded in learning or not. But it's still the same ingredients, still the same picture. And so you define your problem in some usually high dimensional parameterized space. And once you've done that, you run some optimization to solve your problem. So essentially, you can think of it as you have a model, like your hypothesis, the thing that you want to find. You parameterize it. So I already think about some classes of hypotheses, you parameterize them, and then you want to find the optimal parameter. So you use your data and your measure, which goes into this process as your cost function. It spits out some candidate hypothesis, and then you look at this hypothesis with respect to your cost function, and you say, okay, no, this is not good enough. Then update, I pick a new parameter, I go back, I run my model, and I repeat this process until I find a good hypothesis, and I say, okay, now this is good, I accept this, right? So this is kind of like the process. The main difference here is that you're not trying to understand if you can or you cannot learn. You just like try till you succeed. Usually in learning theory, you want to like characterize where you are in with respect to like the hardness of the problem. And I would say like kind of like exact same picture goes into the quantum machine learning realm. When I say quantum machine learning here, now I'm talking about like the quantum version of what people like call machine learning. And so again, you have an unknown object. Again, this object can be classical or quantum now, because maybe you're interested in, I don't know, Hamiltonians or like processes and things like that. And you still have the real world data. Now, the difference here is that if these data are coming from some classical things and you're not directly getting them from quantum processes or like physical experiments, then you need to encode them into some quantum state such that it can run on a quantum computer. And you still have your empirical measure. You have more options here, but usually you can have define like very similar measure to your empirical measure, like a square root, minus square root, or things like that that you're comfortable with, or KL divergence, or all these things that you know. And as for the parameterized part, you're still doing that. Now we just pick a parameterized quantum circuit. So usually it works in this picture that I have here. So this VFX is your layer of encoding. So you can encode your data into this layer. This is your parameterized circuit, and this is your observable, which will tell you like in which basis essentially I want to measure or what I want to observe. And then I do my measurement. And so here your loss function, the nice thing is that you can write it in this very nice expression, which is essentially the trace of your post-process state and your observable. And this will give you like some distance about like where you're going with the problem. So you evaluate that and you repeat the same loop, and you repeat this till you find the answer to your problem. Okay, so I talked about learning, like essentially learning theory, talked about how it connects to practical quantum and classical machine learning. Now I want to go to the crypto realm and tell you like this side of the story. How does things link? So let's start with like conceptually again, what is the goal of cryptography? So cryptography, it's always been about what kind of assumption or which set of assumptions you pick, because you want to show that something is secure or unbreakable. And in order to do that, you always need to assume some. In the modern cryptography, we always like pick some assumptions. So in classical cryptography, these are usually you have two ways. Either you pick some problems that are computationally hard, and then you base your crypto system based on that hardness, or you pick a key that's very nice and random and is as large as the message that you want to work with. And then you encrypt everything with that. But the problem is that you always need to like share this key. So this is essentially like symmetric cryptography and asymmetric or public key cryptography. That's what like the modern cryptography is based on. Then quantum at some point in history came into this picture and kind of like told you that, well, you can do cryptography with no assumption. And well, again, this is not entirely true. You still need to have some assumption. And this assumption is about the physics, right? So if I assume quantum mechanics is the right model for the world, for the physics, then I can do cryptography with no extra assumption. And so this is also not like entirely true. A lot of times in quantum cryptography, you also need to bring some assumption. And then like over time, people have realized that like essentially this field is about finding the best set of assumption to do cryptography with. So you really want to find new ways of doing cryptography using the laws of physics and using like all sorts of assumptions that you can have. And like in order to answer this question that like how we can do like really good cryptography, one thing that we really need to understand is that what is it that makes a secure protocol secure? What is the source of security? Like historically, again, classical cryptographers, they realized that randomness, for instance, is a source of security. You can play around and use randomness in an effective way to design something that is secure. In the quantum world, there is one thing that we know is really deeply connected to security and cryptography, and that's the concept of unclonability. So most of you probably know this with the no cloning theorem that tells you there is no quantum photocopy machine that you can input some quantum state and it will give you the exact same like copies of like two quantum states. So there's no such machine. Quantum mechanics forbids that. And so people realize that this very simple rule of nature, it either directly or indirectly connects to almost all quantum cryptography that we know. So things like quantum key distribution, quantum money, quantum coin flipping, all these like nice quantum protocol that we have in the quantum world. And a lot of other fancier things like zero knowledge proofs, oracles, like all these definitions, one way or another, they all come back to this concept of no cloning, like quantum mechanic forbidding you to be able to make perfect copies of your physical system in forms of a quantum state. And so I think the main conceptual thing that I want to convey here is that this is exactly where things connect to learning. And this is one of the points that very deeply and fundamentally these two concepts come together in the quantum world, and I can extend it to many other things. So okay, let's see how they connect. For that, let's revisit the statement of no cloning theorem, which tells you that if you have an unknown quantum state, that's why here my quantum state is blurry, you have no unitary process that takes you from this to perfect copies of this quantum state, right? So this is my quantum state, and this is physical, like classical description in form of a vector. But if I have the classical description, nothing forbids me to prepare as many copies as I want, right? It's just like prepared, like the unitary that prepares this state, and then I make as many copies as I want. But in quantum information, people have studied the regime in between these two, and this is called approximate cloning. And the idea is that, okay, what if I start with an unknown state and maybe I let like to have copies that are less ideal, so they're not perfect copies of the quantum state, but they're sort of like close to my quantum state. And then quantum mechanics allows that with some probability or some fidelity. And then you can kind of like think about this as a spectrum that I can go from knowing nothing about my quantum state and then allowing some approximation, or I can assume maybe I know some things about my quantum state. So maybe I know that my quantum state is coming only from the equator or something like that. I have some assumptions on my quantum state. And people realize that when you do that, when you have those assumptions, you can actually do cloning better. So you can like have higher fidelity or higher probability of cloning. So this problem of approximate cloning is related to another problem in quantum information, which is how from an unknown state I can estimate the classical description. So essentially, this is a notion of learning quantum state. And I'm going to tell you more about this in the next slide. So what is tomography? Essentially, again, so you have copies of an unknown quantum state, and your goal is to extract the classical description. And so tomography is a very, very old problem. It's a way of like, for physicists, it was a way to be able to characterize like quantum systems. And yeah, so this is like one of the oldest papers about this. But you can think of tomography essentially as a learning problem, just with the exact ingredients that I was talking about. So you have your samples, which are now, your data is like copies of your quantum system. And your concept class is a set of all states that you want to learn from. It can be all pure state or all mixed state, or you can have like certain dimensions that you can restrict this concept class for different problems. And then you spit out some, like the outcome of your learning is some hypothesis that will tell you like some classical description of this state. And your goal is that this approximation is close to my actual state with respect to some distance measure. Usually people pick trace distance, but you can pick fidelity or different things, different distances here. And so exactly, you have a learning problem that given n samples of an n-qubit quantum state, you want to learn this hypothesis with some like this distance less than some epsilon, which will give you the precision. Yeah, so usually you want to know like what is the least amount of copies or sample complexity where you can solve this problem. You can also consider the computation complexity, but usually tomography problems are hard, so like the complexity is usually already like characterized by the sample complexity. So this was for the states, and you can already see that like the better essentially I can learn a state, it seems like the better I can copy it. So there's like this very nice like relation conceptually, at least, between learning and cloning. And in fact, I should say I wanted to update my slide here, but I forgot. But there's a recent paper by Nikhil and Matthias Caro, some of my colleagues in University of Warwick, that studies this problem really nicely and characterizes like the complexity of like relationship between learning and clonability in for stabilizer states. It's a really nice paper. Yeah, after the talk you can ask me about it. I really recommend that paper. Okay, so that was that. But okay, what about processes? And this is, I think, somewhat where things become even more interesting. So what does unclonability mean for a quantum process? So the first attempt, the first time this was defined, it was defined by this nice paper, 2008, by Chiribella. And they define it as, okay, you have two black boxes, O1 and O2. These are your processes. And I define my no cloning in the sense that you don't want to be able to perfectly clone them by single use. So you have this like boxes that you can like query, and on a single use you should not be able to produce the outcome of these two with some like good fidelity. And the key to understand how close learning and unclonability for processes are is to extend like two notions. One is the notion of black box here, and the other one is the notion of single use. So first, if I want to extend my black box, I can just say, okay, there's something that I query, and there's another way of defining a black box, and this is using the notion of like randomness on the unitary group. So I can say, I'm calling something a non-unitary or black box if I query it a random state, a Haar random state, on a single use or whatever time of use I am allowing. I should not be able to distinguish if the outcome is coming from my unitary or if from any other Haar random unitary. And this you can like formally nicely define as a notion of black box or unknownness. Then the second thing you can extend is the single use. So what if I allow multiple use? What will happen? What it would mean is that you have some unknown unitary. You will allow for the cloner to query this unitary multiple times. It will give you some output, and then you don't want the cloning. What it means is that for a new state that you sample from a distribution, you don't want the cloning machine to be able to, or you want, if you want to clone, you want the cloning machine to be able to reproduce the outcome of the unitary on that state. And so essentially, this is a very nice formulation of a learning problem if you think about it, because you have an unknown object, you have some samples that you get from like querying this as a black box, and your target is to learn the outcome of the unitary. And if you cannot do that, essentially that will be like a notion of unclonability. So the extended notion of unclonability can define through the notions of learnability. And so I like to quote this quote of Feynman that says, "What I cannot create, I do not understand." And I think that the moral of what I've been just telling you is that what I cannot learn, I do not clone. So there is like some inherent learning process that is happening underneath any cloning process. And when I know that I cannot like learn things, there's like some notion of unclonability going on somehow. And yeah, so you can again like think about this in this form of like learning theory perspective, that like essentially I have this algorithm that takes the data and want to like spit out like a good hypothesis. And the take-home message is that this like different flavors of unclonability, they can be defined through different notions of learnability. And here is where I can use all these like different learning models that I've been telling you about to tell you like what kind of unclonability I can get for processes in quantum. Okay, so all of that, there's just like some connection, but is this good for cryptography or is it bad for cryptography? And well, the interesting thing is that it's kind of both. And with the time I've left, I'm gonna try to walk you through like where these like different concepts pop up in quantum crypto maybe. Okay, so one important like easy to think about thing is that this is important for cryptanalysis. What do I mean by that? So you can think of a classical or quantum crypto system, and you can always think about a unitary implementation of that, or like you can think of it as like, what if I like implement this process on a quantum computer, let's say. So there's gonna be some quantum circuit that like captures this, and so you can think of any leakage or adversarial behavior towards this crypto system as some sort of interaction that happens between your adversary and the implementation of this model. So essentially, you can learn about the system through interacting with the unitary and get more information from it. And so to be able to understand if this classical or quantum crypto system is going to be secure against quantum adversary, one way to understand it is through understanding how can I learn, or I can learn like things about this like unknown unitary by interacting with it, because this is already gives me a good model of seeing how I, like if I can attack it or not. And if I can make sure, if I can prove that I cannot learn anything, then this gives us like some way of like building good quantum secure crypto system. So this is one way this is relevant. And the other thing is that I've been telling you about different notions of learning, right? And so let's go over like a bunch of them. So first of all, I told you that like you can have this like unitary that I have in my previous picture. You can interact with it in different ways. One way is that you just query, and it will give you the answer. So something like that. Sometimes maybe you can just like get statistics. So you can query this like unitary or like an oracle with some state and some observable, and it will give you some statistics. So these statistics are something like expectation value of your observable after post-processing. And as we were talking about, like, what is my target? I can have different targets about this unitary. So it's not always that you want to learn the full description of, let's say, this unitary matrix. Maybe sometime you want to do that. So that's equivalent of doing full tomography on your process. And maybe sometime you just need to have some worst case distance. You don't need classical description. You just need some objects that like close in some distance, or maybe some like average distance, or you just want to learn the approximation of the outcome, like the previous problem I was showing you. Or maybe you want to learn like, so something that's like on expectation value from some distribution is close to the outcome of your unit. So you can have like different levels of what is this target object that I want to learn. And again, the take-home message is that different results in how well I can learn a certain like classes of unitaries with like good complexities will have consequences in cryptography, because the instance of this problem that I can solve easily and efficiently, then I know that I cannot design crypto systems based on that, because there will always be an attack, a learning attack that learns all this information that I'm trying to hide. And here, note that I'm not specifying what kind of cryptography I'm doing. So I'm not saying it's necessarily encryption or signature, but like whatever it is, I'm just like modeling it as some unknown information being inside this process that I'm like an adversary is trying to extract. Okay, and this brings us to something that I worked on for a while, especially in my PhD. And this is the concept of physical unclonability. So, like essentially, it's a form of unclonability for devices or hardware, and people like had this concept in electrical engineering somehow. And so the idea is that the best way I can describe this is that, let's say you have a factory that produces crystals, right? And in the product line, you see all these crystals that are very, very similar, so they look all the same. But if you look at them very closely and you see all the scattering patterns or all the crystal structure inside that thing, you will know that these are not the same. So these are, in fact, very, very distinct, and you can use that structure as a unique physical behavior. But if I can use this behavior in an interactive way, so maybe if I shine light to this crystal and give me some scattering patterns, and if I can like distinguish this scattering pattern and it's unique, then I can use this piece of crystal as some sort of a key. And this was the idea behind physically unclonable functions, because the idea is that these are unclonable in the sense that these are so uncontrollable and hard that even the manufacturer who makes actually perfect copies cannot make perfect copies. That they're really distinct. And so we brought this idea in quantum to formalize it as a model, and this gives rise to some interesting concept called quantum physical unclonable function, which is essentially nothing but a hard to clone, or if you were following my talk so far, hard to learn unitary. So it's a piece of hardware that you assume like implements some sort of like unitary. You don't have access to that, so it's some sort of like physical black box. You can just like query it with a quantum state, and it will spit out a quantum state. And so the relation with learning comes from the fact that if you can actually learn these things, then they're no longer unclonable. And so how does it work? So let's assume that you have just some database or like some data. You've seen some data of this input and output behavior. So you have some database of talent responses. Let's say you give this into your favorite machine learning algorithms, and it will give you some approximation of the POF model, right? So now, if this is a good approximation, I can give you in a software form as many copies as well. So I can like distribute it amongst you, so you can have like as many copies of this unclonable simile function that you wanted to have, which is now broken because I could learn. And so and this actually happens, and this is the main issues even practically with physical unclonable functions, because essentially people have realized that you can attack them using machine learning and they're not like so secure. And so in quantum, the way we dealt with this is to formalize this like quantum hardware assumption using the fundamental notion of unclonability. And this is exactly what I've been telling you. So using this like nice relationship between unclonability and learnability, and another concept in cryptography, which is essentially very similar to like learning this outcome, which we call unforgeability. Now you can define this like unknown unitaries where no QPT adversary is able to produce on a new input an output which is close to the outcome of the unitary. And so unlike classical POF, you can define this quantum POF and they're provably now secure or unforgeable. So it's not just like some heuristic idea. So you can actually like show things with them and you can use them inside cryptographic proof, and it's really nice. Okay, I'm gonna skip over this so that I can tell you one more thing that is interesting. And yeah, so you can, so this is something we show, and then you can show that, okay, some different variants of this like physical unclonable function, they can be secure or insecure, and the key to understand why they're secure or insecure exactly lies within like understanding how learnable they are. And so for instance, there was some like suggestions about some like nicer to work with physical unclonable functions, and we showed that you can break them essentially because in the quantum world, there are efficient learning algorithms that will allow you to learn the outcome of an unknown quantum process, even if the process is like very hard and complicated. And on the other hand, for the instances that you can show you cannot learn, then you can construct secure protocols. So you can use these things in practice. You can design protocols with them. So we have done things like identification and authentication based on stuff like variants of this problem that we managed to show that it's like hard to learn. And this is how you construct new cryptography from now a hardware assumption that's like purely physical and like relies in quantum mechanics. And so yeah, so this was that maybe design side. And on the other hand, I wanted to say this as well, just like to make more connection for you guys. So cryptography also helps us understand machine learning better. And so one of the goals of like quantum machine learning is for people to understand like for which problem you have quantum advantage for. And essentially cryptography tells you that you have like, it gives you some ways to like pinpoint problems that will be definitely hard. And so we already know this for computation. And the difference between computation and learning problems here is in the data. So the data is the important thing. But there are some really nice works that show you that you can bring constructions from cryptography to make learning problems that you can show that now they're provably hard. Well, now these problems, of course, they're like very contrived and they're not the sort of problems that you see in everyday life, but at least it will give you some proof of existence that there can be things that are quantumly easy to solve and like classically hard to solve. And these are like learning problems and they actually use data. And these are like, there's like some really nice work by the group of Vedran Junko. Again, I don't know why I forgot the citation, but yeah, if you're interested in this, you can have a look. I don't think I have time to talk about pseudo-randomness for you guys, so maybe I'll skip this quickly. And yeah, the only thing I would say is that there's like yet another assumption in quantum cryptography, which is existence of some sort of objects that are easily generatable, but computationally hard to distinguish. And again, this is one of the areas that the link between learning and cryptography becomes like really important, because essentially a distinguisher's role here is to be able to know if you given the distinguisher some like random object or some structured object. And if the distinguisher can learn the structured object essentially in a lot of times, then you can show that you can use this learning, make it into a distinguisher, and then you can break this cryptographic property. So again, this is one of the places where things that are hard to learn are good construction, and when you can find learning attack, you can like break the security and you can show that these are not good constructions. And again, we have like some works about this that we have shown like some constructions and like characterize some resources that you would need for them to be secure. And this is very nice and interesting and very active area of quantum cryptography in the past maybe 6-7 years. They're really cool things here. And so yeah, this is my last slide. Maybe this is like a good way of like wrapping up all these things that I wanted to tell you. So essentially I was trying to like depict this landscape that learning theory is connected to these extended notions of unclonability, which then they connect to cryptography, to modern cryptography, and to doing cryptography from new sets of assumptions, like physical assumptions and things like that, and to the concept of pseudo-randomness, which is again like a very nice and interesting, like different assumption for cryptography. All these things have really deep connections to QML, to even the practical QML, because it will help us like better characterize things that we can or we cannot do in learning. And I really care about this like provability and like evidences that we can find for quantum machine learning. And they have also deep connections between some areas of physics that you might not think that they're connected, like black holes and things like that, which unfortunately I don't have time to talk about. And hopefully once we understand this landscape better, then we can either find really good quantum secure crypto schemes, or we can show really nicely that you have like some advantage in quantum machine learning. And with that, I wrap it up. Thank you so much.
Thank you very much for the interesting conversation and discussion points, Mina. I now welcome any questions. I have set up that people can unmute themselves, so I think just raise your hand if you'd like to ask a question, or if you're more comfortable, you can also post them in the chat for Mina to answer.
I stopped sharing so that I can see you guys, but if you have any questions about any of the slides, let me know. I'll share it back.
Hi, I think while people are busy thinking about the questions, I can maybe ask one simple question. You know, when you started your talk about learning theory, you basically showed that, I mean, it's just a function mapping problem. And the question I want to ask is because basically, I mean, in most machine learning algorithms, you map from some vector space, which encodes your features, and then onto a vector space that encodes your labels or whatever answer that you're trying to extract. Do we know if there's some kind of relationship between the manifolds that this information lives on, you know, the feature space and the output space?
Yeah, in fact, I mean, this is some of the things that, as far as I know, both in classical machine learning and these days in like quantum machine learning, people study. Like especially in quantum machine learning, understanding this like landscape of like your parameterized circuit is important because it's linked to things that we know are limitations of quantum machine learning, like barren plateau or like landscapes that have like many traps essentially. So yeah, the topology, let's say, and geometry of the surfaces are interesting and important in both, I would say, practical sense and in the theoretical sense for provability. Although there's like less work on like in learning theory side about this. Like I found more things again, I guess in the quantum machine learning, people have been like working about this more than in quantum learning theory. But yeah, that's a very good point.
Yeah, because I mean, an interesting question that came to my mind while I was looking at your plots was, does how the manifold changes as you basically map from your input to output state matter? Because the function you learn is essentially also changing the manifolds, right?
Yes, exactly. And it does matter. And yeah, I think maybe I mean, people have started like at least in the quantum and classical. I think there has been studied before, but in quantum setting, people have started looking into how they can use like algebraic topology and things like that to study this like the relationship better and like be able to say things. But it's kind of new, this idea.
Cool. And then another question, I think there's actually two other questions, so maybe I'll just ask this one, then we can check on the chat. Another question I wanted to ask you is, because the way you define clonability at first had to do with states, and somehow you showed that this transfers also naturally to quantum operators. I mean, also, could one actually look at this from the perspective of the Choi-Giacomisky isomorphism, where there's this one-to-one correspondence between unitary operators and states?
Yes, you can use that as I think even in the Chiribella paper they use this to show some bound. But like the reason I'm just like I think there is more to it than just the mere duality between the state and channel. And the reason exactly is because as soon as you move to channels or to unitaries, you can query, and this query will give you, first of all, like if you can query in like multiple times, it gives you like a different problem than if you're thinking about this in a single use. And the second thing is that now you can also query adaptively, which we know that changes learning problems usually, like in some learning problems, adaptivity and the fact that you can, let's say, have all the queries and do something over all the copies, it changes the complexity. And there are like some problems that have this property. So because of that, as soon as you move from a state where you have just like simple access model of just having copies to like processes where you have ability to query them, and that's how you gather your data, you have a lot more like variances of the things that you can get. So the problem already becomes a series of problems, I would say. And that's why it's like more complicated and more interesting. It's not just because of the mapping between state and channels.
I see. Thanks. Jody, I think you can take questions.
Okay, I see somebody has their hand raised, but if I could just go to the chat first, as that was asked first. So there's a question there, Mina, can you see it about unclonability relating to quantum teleportation?
How does unclonability relate to quantum teleportation? Not sure. I mean, the relation is that it's not related to teleportation, but it is related to like usually if for teleportation, maybe the first time like people see this, there's this like seemingly paradoxical thing that like then because I'm measuring this, like I'm measuring and the measurement happens immediately, am I communicating something faster than the speed of light, right? And so then you can show that this is not the case and so on. And like cloning is essentially related in this like to this information bound. So like the fact that you cannot, so the no signaling essentially is related to unclonability. Essentially, if you could, if you didn't have no signaling, then you could have cloning as well. And like even in like more like quantum foundation sense, there are like some extended notion of unclonability where if you allow for signaling models, you can also have cloning there. So that's maybe the best way I can relate it to teleportation.
Thank you. And then regarding the second question, the meeting is being recorded. And if Mina's comfortable, I will then be sharing it. So then everybody will have access. Are you okay with that, Mina?
Yeah, of course.
Great. And then I think if there's more questions relating to this, are you happy for people to reach out to me and I can forward it to you? Or they could also ask Isaac as well if needed, because I know you are from F&B in relation with Isaac. So yeah, if that's okay with you.
Okay, yeah,
and then
sure.
there was one hand which has disappeared. I don't know if that person still has a question. We have 2 minutes. Yes, you can go ahead.
Hello. My question is related to quantum machine learning and the concept of unclonability. So basically, there was a paper I read a few days ago which is talking about we can, after we train the quantum model on a quantum computer, we can then query it to get some classical representation that can be deployed in a classical computer. So then we use inference on a classical computer. So what kind of classical information that can be preserved during this process? Because I feel that the unclonability like forbid us from getting some information classically, right?
Yes, in a way. I mean, that was the relation that I was telling you between no cloning and state estimation, or like tomography, essentially. So if you have like exponential number of copies of your state, you can always like get a accurate, let's say, classical description. And the fact that you cannot do this process efficiently with let's say like polynomial number of copies, it's related to the fact that you cannot clone perfectly or higher than like some fidelity. But I think what you're referring to, and I'm not 100% sure like what paper you're referring to, but essentially like, okay, in learning processes where you have like your states coming into your like quantum machine learning algorithm and so on, and you're extracting some classical information, like for instance, let's say a classical shadow, and you're not necessarily learning the full description. And this is, for instance, one of the very like interesting things about something like a classical shadow, that you're learning some classical sketch about your state that is enough to perform a lot of tasks. Like if you want to learn some expectation value, or if you want to do some certification, or like a lot of things like that. And that is enough, but that information is not enough to do full tomography. So that, for instance, doesn't break the complexity of a full tomography. It just tells you that with a lot less classical information, you can do a lot of things. Like you don't necessarily need the full description for that. And like let me just like share back something quickly to show you something. So in my slides here, when I was, yes, so here when I was telling you like what is it that you want to learn, and like it has like different levels of this problem have different consequences, is exactly something similar. So for maybe some cryptographic scheme, if you can learn the outcome distribution with some approximation, or like up to some distance, that would be enough to break some crypto scheme. Maybe it's not enough for some of them. You would like necessarily need the full description, and maybe the full description is something that's not efficient and you cannot get. But like characterizing exactly what is it that you're trying to learn and why you would need it is, I think, the fundamental answer to your question, because not always you need to learn like the full description, which is usually exponentially hard. But for a lot of tasks, I think like a smarter way of extracting just some information would be enough. And that's essentially how this like inference algorithm work.
Great, thank you. I see there is one more question. Mina, do you have time for one last question?
Yeah, sure.
It is in the chat.
Yes. You can prove. I'm not sure I understand your question. Do you want to elaborate? Sorry, I'm not sure. What is it that's? What do you mean by that you can prove absolute unitary purely statistically? I'm not sure. What do you mean by that?
I'm just checking. I think they may have actually left.
Oh, okay.
Yeah,
Sorry.
actually, I don't think they're around. Yeah. Can I maybe ask Mina like one open question for the audiences that are here? Can you give us your perspective? I mean, what does this mean for future computing and communication systems? We know quantum cryptography in terms of quantum communications might give us provably secure encrypted networks. What does this mean for quantum computing?
You mean that the secure network? What does it mean for quantum computing, or the other way around?
Yeah. So I mean, in communications, quantum cryptography will help us send information securely, like the BB84 protocol, Ethernet protocol. Now, what you're studying here, I mean, does it translate to the same impact for computing as well? As in, we can now run computational algorithms that are basically secure against people trying to steal what we're running on IBM machines or whatever machine we choose.
Yeah, that's a really, really good question. I think one thing that we know by now in the field is that quantum communication is a very important resource if you want to do any sort of secure delegated computation. And so usually all the quantum computing that we know are in the delegated setting. So you send your data to, let's say, Google, right? And we have no control or no verifiability on the things that they will do usually on your data. It's just like give you some answer. Essentially, if your problem is big enough so that you cannot do it yourself, then they can do anything they want. And there are like many protocols. So my PhD supervisor Elham Kaisefi, she done like tons of work on exactly this problem of how can I securely delegate my computation to a server, and how can I, like, after the server has like done the computation and wants to give me back the answer, how can I verify that even though I cannot run the same thing, can I still verify? And this has been a very long-standing problem, which is by now kind of like solved. One thing we know is that in doing this, quantum communication is really important. And like all these like blind protocols, they kind of like use this resource. Like, for instance, you do something like a one-time path on your state and then you send it. There's lots of techniques, but we know that quantum communication is a very important resource. In another, on the other side, one other way that I would say cryptography is really important in computation, quantum communication and cryptography is really important for computation, is because in a lot of roadmaps that you will see in many companies, including IBM, after some point, the systems become distributed. So they're like some processor and they're linked, and this needs to be a quantum link. So it seems that the path towards scalability passes through quantum communication. And so you want, usually in these like extended like quantum computers in the future, you want these devices to be like connected securely, or like have a good quality in the connection, which means that you need to have some level of certification or security, even inside like one, let's say, big quantum computer. So yeah, so I think one thing is the scalability. The other thing is like the verification and security of quantum computation. And for all of these, you need like quantum communication protocols. And the last thing I would say is for learning. And so in fact, this is like some of my latest work about distributed learning, which again, you can see that like quantum communication is an important resource when you want to solve a learning problem, but now in a distributed way. So you have a network, each party have some resource, and then you want all of this party to do something, send the results somewhere and like a central node, they can aggregate everything and learn something. And you want to understand like how this works. And so in all these things, quantum communications are important. As soon as you have that, you will have the issue of the security. So you will need to use some tools from quantum cryptography to make these like settings work in a meaningful way.
Great. Thank you so much again for agreeing to present and for giving such an interesting presentation, Mina. And thank you again for everybody who attended, and we hope to see you in future seminars. Have a good rest of your afternoon.
Thank you so much. Thanks for having me. Bye-bye.
Bye.